which is just across the hall. That one. Okay, now, how did the practice test go? Was it hard? Five? Okay. I was going to run through it. So, do that. So the first question is totally bound, define totally bounded. If a space is totally bounded, who would be a countable dense subset? Okay, so totally bounded means each epsilon greater than 0, there exists a finite number of balls of radius epsilon centered at certain points. So that the metric space is the union from 1 to n of these. I guess I'm using n. So that's totally bounded. And now we want to show that a totally bounded metric space has a countable dense subset. So we can choose, since this is supposed to work for all epsilon, we can choose epsilon successively to be 1 over n. So apply with epsilon equals 1 over n. Then there exist points, I don't know how many there are, but a finite number. So x sub, so we'll index it by n, x sub n1 up to x sub n, and then some integer depending on n. Such that the ball neighborhood of radius 1 over n centered at x sub n case I, union I equals 1 yes, so this should be sub I equals 1 to k sub n. The notation is getting away from me. Such that this is equal to x. So for each n, we have only a finite number of points. When we put them all together, we still have a countable set.
Is it that it is equal to, or that it is, that x is contained?
It's the same thing, though, because x is our universe.
Okay.
So we can't have anything bigger than x.
Okay.
If we're just saying x is our metric space. So it's equality here. Okay, so the xni's form a countable set. And now we want to show that these are dense. So for any other point at any epsilon, we should be able to get epsilon close using one of these points. So given some point y in the metric space, epsilon greater than 0, let us choose n so that 1 over n is less than epsilon. Then y, since the union of the corresponding neighborhoods is the whole of x, y is certainly in the union. By definition of totally bounded, and therefore, for some I, the distance from y to x n I will be less than 1 over n, which will be less than epsilon. So we can get epsilon close to any point in the metric space from this countable sector. And therefore, the set of xni's is going to be dense. Any questions about this one?
Is there like another like general strategy where you show the set of the x and i's is intersected with the ball around y is non-empty? Is that?
Let's see. Could you do it that way? Yes, it would amount basically to the same thing.
But it has to be the closure, though.
Well,
No.
density just means that you can come epsilon close to any point. It's the same. It's the same. The definition is that the closure should be the whole of x. But if you have any point in x, any ball centered at that point is going to intersect, is going to contain one of the twice of ni's, and so the closure will be the whole thing. Anything else?
Do we need to bring anything?
Oh, yes. If you would bring a blue book. Everyone know what a blue book is? I don't even have one. This is a blue book. Some of you, if you're new to the campus, may not know. Anyway, they're available in the bookstores, also any of the convenience stores on campus or around campus. So they're available everywhere. Right, let's move on to number 2. Okay, so sequentially compact. Sequentially compact, the definition there is that every sequence in the metric space has a convergent subsequence. Then we're asked to prove directions. So let us assume that E is closed. Now we have to prove that every sequence in E has a convergent subsequence that converges to something E. So take a sequence xn in E. Now use the sequential compactness of the whole space to say that this has a convergent subsequence. So by sequential compactness, of X, there is a subsequence xnk converges to a point X in capital X. But now the fact that E is closed says that with sequences you can never get out. If it's converging, the limit ends up inside E. So since E is closed, this limit that exists because of the sequential compactness of the big space will force the limit to be inside E. And so we have verified the definition of sequential compactness for E. So therefore, E is sequentially compact. Now, in the other direction, now we assume that E is sequentially compact. Now remember that the closure of a set is the set together with all its limit points. So if it is not closed, then there will be a sequence from E that converges to something outside E. So we'll argue by contradiction. If E is not closed, then there exists a sequence xn in E converging to a point X in the complement of E. Well, by the sequential compactness of E, any sequence that you have in E has a convergent subsequence with limit infinity. There is a subsequence xnk converging to a point, we've already used X, converging to a point Y in E. But the sequence was already converging inside X, so any subsequence will converge to the same thing. Therefore, therefore xnk converges to, on the one hand, x in E complement, and also y in E. This is impossible. A sequence will have a unique limit. It's either in one or the other. So we have a contradiction here. And it contradicted the assumption that E was not closed. So therefore, E is closed. Is that okay?
You mean every sequence that converges has a unique limit, right?
Right.
Not, and you just said every sequence. Okay. I was confused.
Okay. I meant what you said, but maybe I didn't say that. So any sequence that converges to some limit has only one limit. Any other questions about this?
Just that this side of the statement doesn't really use compactness of capital X, right?
Well, sequential compactness is the same as compactness.
I know that, but it's just using the compactness of E, not of X. Like this side of the statement doesn't really matter if X, capital X, is compact or not.
Right, let's see. If it's sequentially compact,
No, but he's saying it doesn't use the whole space, he just uses the subspace.
yeah, we're really just using E. Yeah, so it just depends on the E, not the sequential compactness values. So the third problem. Okay, we've got a complete metric space, state Bayes' theorem. So Bayes' theorem says that if X is complete, and U1, U2, etc. are open dense sets, then the intersection of them is also dense. So we're going to use it in the form X cannot be written as a countable union of nowhere dense sets. So we are given some sets. So we have a sequence so Fn is a sequence of continuous functions on 0, 1. And they converge pointwise to 0 for each X. Epsilon greater than 0 is given. And we look at the following set of x's in 0, 1, the property that the absolute value fk of x is less than or equal to epsilon, k greater than or equal to n. each En is closed, and then that there is an open interval and an integer capital N, so that that inequality holds. Okay, so for a fixed N, since we want to show that En is closed, consider a sequence xm in E sub n with xm converging to x. We have to verify that x is in this set by continuity of the function for each k greater than or equal to n. We have that fk at xm in absolute value is less than or equal to epsilon for all n. Now, if we let m go to infinity, and use the continuity of fk, we get that the absolute value f sub k of x is less than or equal to epsilon, and that is going to be true for any k greater than or equal to n. That verifies the definition of membership in En. Therefore, x is in En, so En is closed. Now, we would like to see that every point in 0, 1 belongs in some En. So, let us now fix an x in 0, 1. Then, because of the convergence of the sequence pointwise to 0, you can say that given epsilon greater than 0, there exists a capital N, so that the absolute value fk of x is less than epsilon over 2, no, just epsilon will work, less than epsilon for k greater than or equal to capital N. So that is just convergence of the sequence f sub k of x to 0. Well, we have strict inequality, but that implies less than or equal to. And therefore, this point x is in the set that corresponds to capital N, so E sub capital N. And therefore, each point in 0, 1 is in one of these E sub n's at least. And therefore, x is the union from 1 to infinity space that's written as a countable union of closed sets, they cannot all be nowhere dense. So at least one of them is not. And that means that it contains an open set, and hence an open interval. So by there, X E sub some E sub n contains an open interval. And that's what we need. Because then, I guess we should write it as E sub capital N. And therefore, X in the interval I and n greater than or equal to capital N, we get that the absolute value Fn of x is less than or equal to epsilon. So it's something like uniform convergence. At least there is an interval on which you get within epsilon of the limit for all the functions beyond a certain point simultaneously. So that's the conclusion here from Bayes' theorem.
Sir,
Yes.
at the very beginning, since all of the k's, all the f of k's, they map to the closed interval negative epsilon to epsilon, and f is continuous, couldn't you just say that the preimage is closed, and then En is the intersection of all the preimages, so that's closed too?
Yes, you could do that. That would be fine. Okay. I think it's time to do both, so let's do question 4 next. So we've got, first of all, the Euclidean norm. And we have to prove that if 0 is less than or equal to A less than or equal to C, and 0 less than or equal to B less than or equal to D, then the 2 norm of AB is less than or equal to the 2 norm of CD. So this is straightforward because the 2 norm of AB squared, to prove this inequality, since everything is non-negative, it's enough to prove the inequality with the square there. So this is A squared plus B squared, which will then be less than or equal to C squared plus D squared, and that is the 2 norm of CD squared. And then part B, now we've got a set with 2 metrics on it, E and rho, and then we define a third thing. So sigma of xy is the 2 norm. If you take the distance dxy and the distance rho xy, those are 2 numbers. So we form a 2 vector and take its 2 norm. We want to show that that is a metric. So first of all, it's clearly non-negative. It's the 2 norm of the vector. Secondly, it is 0 if and only if the vector has norm 0, which means that the entries here must both be 0. And that's equivalent to x equals y. Because although we don't know sigma as a metric yet, d and rho certainly are. Then we need that interchanging x and y gets you the same distance. So sigma of xy is the 2 norm of dxy rho xy. And now for d and rho, since those are metrics, you can interchange the order of x and y. So this is the 2 norm of dyx rho yx, which is sigma of yx. So these are the 3 that are usually trivial to verify when you're checking that something's a metric. If there are any problems at all, it comes with the triangle inequality. So let's have a look at the triangle inequality. Now, sigma of x to z is the 2 norm of d of xz rho of xz. And we also know that we have the triangle inequality for d and rho. So d of xz is less than or equal to d of xy plus d of yz, and rho of xz, no, yes, it's rho. So we have that. So by part A, where A corresponds to d of xy, C corresponds to d of xy plus d of yz. These are all non-negative and one's bigger than the other. So by A, the 2 norm of d of xc rho of xc is less than or equal to the 2 norm of the vector d of xy plus d of yz. Same thing with rho. We get that. Now this is just the sum of 2 vectors. Here's the first column, and here's another column vector. So we can use the fact that the 2 norm is a norm to say that this is less than or equal to the 2 norm of dxy rho xy plus the 2 norm of d of yz rho of yz. So we've used that d and rho are metrics to get to here, and then we use the fact that the 2 norm is a norm to get to here. But this is sigma of x, y plus sigma of yz. So there we have the triangle inequality for sigma. So sigma is a metric. finally, number 5. Okay, so completeness is just the fact that every Cauchy sequence converges. And now we have the space called little c0. So little c0 is the set of sequences x1, x2, so on, with the property that xn tends to 0. Of course, if you have a convergent sequence, it's bounded. And since it's going to 0, you actually have a maximum of the absolute value. And so the norm of the sequence x1 and so on is the maximum of the absolute values of the xi's. I agree. So to show completeness, we have to show that every Cauchy sequence converges. So let capital Xn be a Cauchy sequence in little c0, and x capital N. The main obstacle in these problems is notation. So the nth sequence should be little xn1, little xn2, little xn3, and so on. Now, since it's Cauchy, we can say, given epsilon greater than 0, there exists capital N so that the norm of x sub n minus x sub m is less than epsilon for m and n greater than or equal to capital N. Now, using the definition of the norm, in other words, the maximum of the absolute value of xn k minus x mk, maximum taken over k, is less than epsilon for m and n greater than or equal to capital N. And that tells us that in any particular coordinate, first coordinates, second coordinates, third coordinates, and so on, we have a Cauchy sequence. So we have a Cauchy sequence in each coordinate. Now, the coordinates are just real numbers. So if you have a Cauchy sequence of real numbers, it's going to converge to something. So we get that the limit over n, x, n, k, exists for each k. x of k, and define a new infinite sequence by capital X is equal to x1, x2, x3, and so on. So that is the candidate for convergence of the sequence capital Xn in C0. So two things to prove. First of all, that is in C0. And secondly, that we have convergence to it. Okay, so first thing we have to do is that the sequence capital X is in little c0. So we want to show that beyond a certain point, its coordinates are all less than epsilon. So given epsilon greater than 0, for m and n greater than or equal to capital N, we have that the absolute value of x n k minus x m k is less than epsilon, and that is for m and n, this is for all k greater than 1. So in this inequality, let m go to infinity, and what we get is that the absolute value of xnk minus xk is less than or equal to epsilon for all k greater than or equal to 1. And for all n greater than or equal to capital N. So let's just fix little n as capital N. So x capital N k minus x of k is less than or equal to epsilon for k greater than or equal to 1. But this sequence, for a fixed n, letting k vary, that's an element of little c0. So the sequence x capital N1, x capital N2, and so on, is in C0. So far enough out, all the terms are less than epsilon. So there exists capital K so that the absolute value x sub capital N k is less than or equal to epsilon for k greater than or equal to capital K. That's just membership in C0. Okay, so the differences are bounded by epsilon, and these first terms are also bounded by epsilon, and therefore the absolute value of xk is less than or equal to 2 epsilon for k greater than or equal to capital K. And therefore, our candidate is actually in C0. Therefore, the sequence x1, x1, x2, and so on, is in little c0. Okay, so let's go back to this point. Let's call this star. If you think about what star says, it says the differences of coordinates are uniformly bounded by epsilon. Star says that the norm of capital X sub n minus capital X is less than or equal to epsilon for n greater than or equal to capital N. And therefore, capital Xn, now that we know that capital X is in C0, that converges to capital X in C0. So it was a two-step process. We first of all had to find a candidate for the limit, basically by seeing that we could take a limit in each coordinate. And then we had to show that the original sequence converged to our candidate. And along the way, we had an inequality that would guarantee that.
Is it true, is every space, subspace have a complete space?
Yes, it is.
So can we not just say that it must exist since it's in the higher space, since the higher space is complete, and then prove that it converges to it?
But we wouldn't know it was in C0.
But I mean, okay, so if you have C0, you know that there is a space which is complete, which contains C0. Therefore, you must have that in the higher space and prove that, and then be able to prove that that is actually in C0.
Yes. Yes, okay. You could do that.
Well, it's like if you have an open sample, you don't know if the limit is.
Right, so yes, you'd have to prove independently that it's in C0.
Yes, but you know that it exists
Right.
in the higher space.
I have not talked about this, but there is a general theorem that says if you start with any metric space, then you can embed it as a dense set in a complete metric space. The construction is kind of ugly. What you have to do is you look at the spaces of Cauchy sequences and you identify a point in X with the constant sequence X, 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 X. And then you put a metric on the distance between any two Cauchy sequences, and then prove that the Cauchy sequences with this metric are complete. So, it's not pretty. When you prove that, you quickly run out of subscripts. Okay, so we're out of time. One last reminder, the exam changed the room. It's a better room over there. I didn't think I could get one, but after announcing we were going to have it in Milner, I got back to my office and found that they'd come up with a room for me. So it's just across the corridor, 119B. And please make sure you bring a blue book. And also, you can bring some scratch paper as well, just for the